So we've already seen how to use logs to solve exponential equations. Now let's start with a logarithmic equation and use an exponential to solve it. So again, remember log base answer equals exponent. If we want to solve this using a translation method, what I would do is just translate this directly into an exponential equation. So that would be the base is 7 to the exponent 2 equals the answer, 3x minus 2. So now this is an equation I know how to solve. 49 equals 3x minus 2. This is just a linear equation. Divide both sides by 3. You get x equals 17. Or is it? Yeah, 17. All right, now, one tricky thing. Because there are certain numbers that you're not allowed to plug into the logarithm has a limited domain. So we need to remember that the domain of, say, log of x is equal to the set from 0 to infinity. It's all positive numbers. So you're not allowed to plug 0 into the logarithm. You're also not allowed to plug any negative number into the logarithm. So I do need to double check that this value, because sometimes when you are solving logarithmic equations, you get answers that aren't actually answers. So what I'm going to do is I'll check my solution by just plugging it back in. And of course, if I'm using a calculator that doesn't have the log base button, I'll just use the natural log. So I'll say natural log of 3 times 17 minus 2 over natural log of 7, which is the same thing as log base 7 of 3 times 17 minus 2. And I'll check to see if that's equal to 2. Let's see. Natural log 3 times 17 minus 2 over natural log of 7, and I get out the value 2. So this does work. So now I know for sure that's my answer. So this was one method, using translation to solve the equation. Method 2 is to apply the inverse of the logarithm to undo the logarithm. So apply the exponential to both sides, obviously. All right, so if I have log base 7 of this equals 2, what I'm going to do is I'll start with the base 7. I'll say 7 to the power this whole side, log base 7 of 3x minus 2 equals log base 7, or sorry, not, exponential base 7 of this whole side. So 7 to the power 2. Okay, in doing that, the exponential base 7 and logarithm base 7, they cancel each other out, and this 3x minus 2 comes down, and I get 49 on this side. And of course, adding to dividing by 3, I again get 17 as my answer. Okay, so you see I have two methods. One is more like using the elementary properties, and this method, applying the exponential to both sides, which really does undo the logarithm. This is maybe a more sophisticated method. Let's try another example. Log base 5 of x equals log base 5 of 2x plus 3 minus log base 5 of 2x minus 3. So a few things happening here. First of all, I want to notice that I'd like to combine these two as a single logarithm, because if I apply log base 5 to this side, that's not going to help me because I don't have any rule for taking a log of a difference. So I'm going to compress this together first. So let me just start with log base 5 of x equals, and the difference of the logs is the log of the quotient. Numerator is 2x plus 3. Denominator, 2x minus 3. Okay, and now there's a few things we could do. Now that I have it written as a single log, I could notice that it's the log with the same base, so just set the insides equal to each other. You can convert this, or you can use that other method, which is apply the exponential base 5 to both sides. So the way I write that is generally I'll put like a large 5 here. This means 5 to this power equals 5 to that power. So this whole expression now has like kind of gone up a level into the exponent. And then, knowing that these are inverses of each other, exponential base 5 to the power, log base 5, those undo each other and you just get x. Same thing over here. Those inverse functions undo each other. Okay, so great. Now I've gotten rid of all logarithms, no exponentials, no nothing. So now what I want to do is just solve this equation. I should notice that I don't want this denominator to be 0, right? But let's go ahead and solve this by multiplying both sides by 2x minus 3, which will kill that denominator for me. Just like that. Let me go ahead and expand this out. I've got 2x squared minus 3x equals 2x plus 3. Now I have to reevaluate what type of function is this. Well, it's a quadratic, so the way we solve those is get everything to one side, 0 on the other. So let's go ahead and subtract 2x from both sides, subtract 3 from both sides. I get 2x squared minus 5x minus 3 equals 0. All right, now this quadratic equation, you can solve it really any way you want. You can factor, you can use the quadratic formula, whatever you like. I think I'm going to factor. I'll use the AC method, which is like what two numbers multiply to give me 2 times negative 3, the A times the C. So multiply to give me negative 6, and add to give me the middle number, negative 5. So I know that's got to be negative 6 times positive 1, right? So let me go ahead and rewrite this middle term. 2x squared minus 6x plus 1x minus 3 equals 0. So all I did was rewrite that minus 5x using these two special numbers. And now I can factor by grouping. Look at the first two terms. They have a 2x in common. Let me go ahead and pull that out. What I have left from this term is an x. What I have left from the minus 6x is minus 3. And then I look at the next two terms, x minus 3. They don't have any factors in common other than 1. Might as well throw a 1 out there. And then you notice that you have this common factor of x minus 3, which you can pull out. What I have left is a 2x and the 1. Whew. Okay, that was kind of a lot of work just for factoring. Now let's go ahead and set these two equations to 0. These two factors to 0 to get my solutions. So I have x minus 3 equals 0, which gives me x equals 3. And I also have 2x plus 1 equals 0, which gives me x equals negative a half. Okay, now you can go ahead and plug these values into the original equation, see if you get that it's the correct solution. But I just want to point something out. I'm not even going to do that with this number, x equals negative a half, because I already know since x is negative here, negative a half, if I plug it in here, I'm going to get an error. If I do log base 5 of negative a half, that won't give me anything. So I know for sure that that answer is wrong. So why don't I go ahead and check the other answer, x equals 3. So I'll do log base 5 of 3, and I'm going to see if that's equal to log base 5 of 2 times 3 plus 3, minus log base 5 of 2 times 3 minus 3. And then to use my calculator, I definitely want to rewrite this using natural logs. So I mean, natural log of 3 over natural log of 5 equals natural log of, what is it, 679, 9 over natural log of 5 minus natural log of 6, 5, 4, 3 over natural log of 5. Notice I didn't have any weird things going on. I'm not like, I don't see any zeros or negative numbers inside these logarithms, so I have a feeling that this is going to work out okay. Let's go ahead and check. So on the left, I've got natural log 3 over natural log 5, which gives me approximately 0.68. And over here, natural log of 9 over natural log of 5 minus natural log of 3 over natural log of 5. And I do get the same exact number, so it checks out. So I know for sure that my answer is x equals 3. All right, so let's just go over our method again. Number 1, it's always important to check your answers, like always. But some instances are more important than others. So when you're dealing with a logarithm equation, because you have a restricted domain, you definitely want to check your answers for these problems, okay? And we have a couple methods. You can translate directly to an exponential equation, or you can apply an exponential with the same base to both sides to undo that exponential.